Welcome back to another episode of Tech Talk Today. I'm your host, and today we're diving into a really intriguing topic that sits at the crossroads of data consistency and system performance: linearizability. We'll unpack what linearizability actually means, its impact on system design, and the trade-offs that come into play when implementing it in distributed databases. So grab your headphones and let's get started. To begin with, let's clarify what linearizability is. At its core, linearizability is a consistency model that makes sure operations on a data object seem to happen instantaneously at some point between their start and end times. Picture this. You're at a coffee shop and you order a latte. Linearizability ensures that everyone sees your order in the same order, no matter when they check the order board. This is especially important in distributed systems where multiple nodes might be accessing and modifying the same data. Now let's see how this concept plays out in real-world applications. Consider a scenario involving a web server and an image resizer. When a user uploads a photo, the web server doesn't send the entire image through a message queue because that would be quite inefficient. Images can be several megabytes after all. Instead, the photo is first stored in a file storage service. Once that's done, an instruction is sent to the image resizer via the message queue. Here's where things can get a bit tricky. If the file storage service is linearizable, everything runs smoothly. But if it isn't, we risk encountering a race condition. This means the instruction to resize the image could be processed before the image is fully written to storage. As a result, the resizer might fetch an outdated version of the image, leading to inconsistencies between the full-size and resized versions. This scenario really highlights why linearizability is crucial for maintaining data integrity across different components of a system. Let's talk about how we can achieve linearizability. The simplest method might seem to be relying on a single copy of the data. However, this approach isn't fault-tolerant. If that single node fails, the data could be lost or become inaccessible. Instead, we often look to replication methods to ensure both availability and consistency. One popular approach is single-leader replication, where one node acts as the primary source for writes, while others maintain backup copies. If reads are performed from the leader or from followers that are updated synchronously, we can achieve linearizability. But not all single-leader systems guarantee linearizability due to issues like snapshot isolation or concurrency problems. On the flip side, we have consensus algorithms, like those used in systems such as Zookeeper and etcd. These algorithms are designed to prevent problems like split-brain scenarios and stale replicas, allowing them to implement linearizable storage safely. This makes consensus protocols a strong choice for ensuring data consistency. However, multi-leader replication, which allows for concurrent writes across multiple nodes, generally doesn't support linearizability. This method can lead to conflicting writes that need resolution, which goes against the linearizability requirement of having a single, consistent view of data. Then there's leaderless replication, often seen in systems like Dynamo. While some argue that strong consistency can be achieved through quorum reads and writes, this can be misleading. Using time-stamped conflict resolution methods like last write wins can lead to non-linearizable behavior due to clock skew. Now let's consider the implications of network interruptions. In a multi-data center setup, if a network issue pops up, clients in one data center may lose the ability to communicate with the leader in another data center. This means they can't perform linearizable reads or writes, which could lead to downtime. While clients can still read from their local data center, those reads might be stale. This brings us to the CAP theorem, which states that in the presence of a network partition, a distributed system can only guarantee either consistency or availability, but not both. If your application requires linearizability, it might become unavailable during network issues. On the other hand, if it doesn't require linearizability, it can continue to operate independently, even when some nodes are disconnected. The CAP theorem has really shifted how we approach database design. It encourages engineers to explore a broader range of distributed system architectures, particularly those that are more resilient and better suited for large-scale applications. This shift has led to the emergence of NoSQL databases and a variety of new technologies that prioritize availability and partition tolerance over strict consistency. So what does all this mean for developers and system architects? Understanding the trade-offs between linearizability, availability, and partition tolerance is crucial when designing systems. Each application has unique requirements, and the choice of replication method and consistency model should align with those needs. In summary, linearizability is a vital concept in distributed systems that ensures a consistent view of data across multiple nodes. While it can be achieved through various replication methods, each comes with its own set of trade-offs. Your decision on whether to prioritize consistency, availability, or fault tolerance will ultimately shape your system architecture. Thanks for tuning in to this episode of Tech Talk Today. We hope you found this discussion on linearizability insightful and that it helps you navigate the complexities of distributed systems in your own projects. If you enjoyed today's episode, don't forget to subscribe and leave us a review. Until next time, keep exploring the fascinating world of technology.